Welcome to an introduction to calculus, the first lesson, lesson 1.1. Before you take the note for 1.1 contained in this video, make sure you've read pages 6 to 8 of the textbook and skim through the questions you'll be doing after the lesson. Pause the video until you've done that. Once you're ready to begin, continue. Well, radicals are really roots, square roots, and nth roots, cube roots, that sort of thing, right? So the square root of a times the square root of a is a. The nth root of a raised to the power of n is a. So that's like the cube root of 8. All cubed is actually 2 cubed, which is 8. That's what it means. And finally, the third point here is that the nth root, right? The root is a denominator, and the power is the numerator. You can either do the power before you take the root or take the root and then raise to the exponent, the power. And n is even, then a must be greater than 0. If n is odd, then a could be negative. Okay, you can't take the even root of a negative. You can't take the square root or fourth root of a negative number, for example. Okay, so give these examples a look, and once you're ready to begin, roll the video. Square root of 3 times the square root of 3 is 3. So breaking this apart, or changing it, I'm going to bring the cubing inside, and then I'm going to break it into two parts. So the square root of 5 cubed is the same as the square root of 5 squared times the square root of 5. Square root of 5 squared is 5 times the root of 5. Now try the next one. So pause the video until you've tried the next one. Okay, so cube root of 7, and I'm going to break it apart right away. It's the fifth power of 7, right? So I'm going to say it's 7 cubed times the cube root of 7 squared. So that'll be 7 square root of 49. Rationalizing denominators, right? Proper form, the denominator is rationalized. We're also going to use rationalizing to simplify expressions when we're finding limits, okay? But it's still a skill to rationalize the denominator, to have things in proper form. So we multiply, we have a over the square root of over b times the square root of c. We multiply by a special version of 1, right? We're allowed to multiply by 1. And what happens when we do that is that the square root times the square root and the denominator, we end up with c. The root of c times the root of c is c. And we ended up with the radical or the square root in the numerator instead. So what's the special version of 1 that we multiply this example by? Well, we want to get rid of the square root of 5. So we're going to multiply by the square root of 5 over the square root of 5. So in the numerator, we'll have 2 times the root of 5. In the denominator, we'll have 3. Now the root of 5 times the root of 5 is simply 5. So 2 root 5 over 15. Conjugate radicals are where you change the sign. If they're positive, you make them negative, and negative to positive. Just take a look. They're the same. It's also a sort of a difference of squares idea, which we're going to get to in a minute. So state the conjugate radicals. So it'll still be, it's not equal to, right? The idea is it's a conjugate, not equal, but a conjugate. So it's 2 in root 3. We're starting with plus, so now it's minus. Root 2 in root 3. We're starting with minus, so now it's plus. Pause the video, do the last two, and then go. Confirm. Okay, so exactly the same terms, just switch the sign. And as I was saying, that's the difference of square patterns. If you multiply conjugates, you end up with this difference of squares pattern. And that's useful because it eliminates radicals. So see how we have a plus and a minus, right? A minus and a plus. So it'll be a squared minus the square root of b squared. So it'll be a squared minus b. Pause the video and do the other two. Square root of a squared is a. Square root of b squared is b minus a minus, notice the b is not inside the square root, so it's b squared. The square root of c times the square root of c is c. So to rationalize the denominators, we multiply and divide by the conjugate radical of the denominator. So taking a closer look at the first one, we're going to multiply by a special version of 1 that contains the conjugate for the denominator. So that'll be 1 plus root 2, and it's a special version of 1, so the numerator has to be exactly the same thing. So the distributing in the top, it's 3 plus 3 times the root of 2. And the denominator, we have the difference of squares pattern, so it'll be 1 minus 2. Simplifying, 3 plus 3 root 2 over minus 1. So negative 3 minus 3 root 2. Pause the video and try B and C. Okay, if you're ready to begin, the conjugate is 2 minus 3 root 5. So the numerator and the denominator have to be exactly the same thing. Distribute in the numerator. Difference of square pattern in the denominator. 3 squared is 9. Root of 5 times root of 5 is 5. 2 minus 45 is negative 43. Oh, 2 times 2 is 4. Negative 41. There we go. And for C, the conjugate would be root 3 plus root 6. So a special version of 1, numerator and denominator is the same. 2 root 3 plus 2 root 6 over 3 minus 6. It's negative 3 in the bottom. I didn't do it on the last one. Maybe we should. We'll put the negative out in front. 2 root 3 plus 2 root 6 in the numerator, and that's done. Now, proper form in general math is to have no radicals in the denominator, so we rationalize. But in calculus, we're not just looking about proper form. We're looking at simplifying certain things. So sometimes you'll actually be trying to rationalize the numerator, in which case you multiply by the conjugate of the numerator. Okay, so to rationalize this, we multiply by to rationalize the numerator, we multiply by the conjugate of the numerator. So that's root 5 plus root 3 over root 5 plus root 3. So 5 minus 3. And the denominator we have this to distribute, but we don't have to FOIL it. We're actually going to leave the denominator factored. The whole point is to simplify in the numerator. That's why we're doing it in calculus, not to actually rationalize it. So we're just going to leave it like that. You may get equivalent expressions by rationalizing the numerator or denominator, and sometimes you might even do both. So we're just going to be simplifying by rationalizing, and we have to state the restrictions. So no numbers this time. Well, there's some numbers, but there's also lots of algebra here. So we're going to multiply by the conjugate of the denominators. So square root of x plus 1, square root of x plus 1. Now, we're not going to FOIL in the numerator. We're just going to leave it because we're hoping something's going to simplify out. So look at the difference of squares pattern, right? We're going to have square root of x times the square root of x is x. And 1 times 1 is 1 minus. And there's why we didn't bother FOILing in the numerator. We're trying to cancel that. This simplifies to the square root of x plus 1. And of course, we have to state restrictions. First of all, x cannot be equal to 1 for the denominator, but x must also be greater than or equal to 0 because we can't take the square root of a negative. All right. This time we're going to rationalize the numerator. So the conjugate is what? Well, it's a more complicated expression. So it's the square root of x plus 9 minus 3, so we have a 3, but it's a plus sign there. And again, don't simplify the denominator. See if we can get something to cancel out. So in the denominator, we still have x. We have the conjugate that we came up with in the denominator as well. In the numerator, we use the difference of squares pattern, so it'll be x plus 9 minus 9, right? 9 minus 9 is 0. X over x, they cancel out. We end up with 1 over the square root of x plus 9 plus 3. Now, what has to be true for the restrictions? Well, x cannot be 0. That's right. And we can't take the square root of a negative, so x plus 9 must be greater than or equal to 0. So x must be greater than or equal to negative 9, right? Because we have x plus 9 in the square root. Okay. All right. When you're ready, take a look at C. Now, this is by far the most intense one because it's not only radical expression, but it's also rational in that it's 1 over the square root. So the conjugate here is 1 over the square root of x plus h plus 1 over the square root of x. 1 over x plus h plus 1 over the square root of x. Now, when we simplify this, there's a couple of things we have to worry about. We have to take care of fraction things, but we also have to take care of the radical. But the first thing to think about is that we're not going to simplify in the denominator. We're just going to work in the numerator first. So in the denominator, I will simply have this. Right, with that conjugate there. In the numerator, it's the difference of squares pattern. So it'll be 1 squared, which is 1, x plus h, the root of x plus h squared, so x plus h, minus 1 squared over the root of x squared, so that's x. Now, in that numerator, we want to come up with a common denominator. So for the numerator, that'll be x plus h. So the first term, we're going to multiply by x over x, a special version of 1. Second one, x plus h over x plus h, right? So that we have a common denominator. We end up with x minus x plus h. And we're dividing by that denominator, right? So we multiply by 1, the reciprocal. So, and it's just a way to keep the denominator simplified. like. So what else do we have happening here? Okay. So for the next step, x minus x, we have negative h over h. So, right, h over h cancel out. So we end up with negative 1, right, left over. And also in the denominator, we have this x. We have this x plus h. The h here was canceled, so we just have this conjugate part here. And now we have to state restrictions. X plus h must be greater than or equal to 0. Well, can't be 0 because we'd be dividing by 0, so x plus h must be greater than 0, so we don't take the square root of a negative, and we don't have 0 in the denominator. That's from this part here and here, for example. H cannot be equal to 0 because we have that in the denominator. And x can't be 0 because we have it in the denominator, but we also have the square root of x, so x must be greater than 0. So there's all the restrictions. And then we get to the last part. So difference of cubes. Sum of cubes. Remember the pattern from advanced functions. And this, they're showing, they sort of skipped a step. There should be a step in here, right? This is a difference of squares. And then the result of that is, again, a difference of squares, so we can factor this again to get these two parts right there. Okay, so let's see how we can use that in something more interesting. Now, there's a hint here that we're actually looking at a difference of cubes, right? So one way to think of it is that we're going to let a equal to the cube root of x, and therefore a cubed is equal to x. Okay, so put a let statement there. Translating this first one, we actually end up with a cubed minus 1 over a minus 1. So the difference of cubes is a minus 1, a squared plus a plus 1 over a minus 1. The a minus 1s cancel out, right? Leaving us with a squared plus a plus 1. Now putting back x, we have cube root of x squared plus the cube root of x plus 1. And of course, a cannot be equal to 1, so x cannot be equal to 1. So this will be a squared minus 1, a squared plus 1. Sorry, not a, x. So just difference of squares in the numerator to start, difference of cubes in the denominator. Factoring the numerator a little bit further. The x minus 1s cancel, leaving x plus 1, x squared plus 1, or x squared plus x plus 1. And of course, x cannot be 1. Well, that's the end. Be prepared to, we'll take a look at the questions on page 9 that were assigned, and then we can take up any problems in class. Be prepared to ask questions, okay? All right, we'll see you in class.